All right, so now let's get into our first addition reaction here. These are hydrohalogenation reactions. So hydro, meaning one of the things we're going to be adding is a hydrogen atom. And then halogen, one of them is going to be chlorine, bromine, or iodine, right? So these are these hydrohalogenation reactions. So let's take a look at, again, notice that these are going to be at relatively low temperatures because we're going to try to favor that, that addition product as opposed to the elimination product. And so all of these reactions, these addition reactions, they're all about adding new bonds to those vinyl carbons, right? So these reactions will break this double bond and we'll have an addition to two of these vinyl carbons. One direction, or rather on one of them, we'll have our hydrogen, and on the other one, our bromine, right? So our simple addition product here would be this alkyl halide. And then just to be really good at pointing out what's going on here, this hydrogen on this side, which is of course implicitly drawn, so we don't draw it explicitly, but this was originally that hydrogen. And of course that boron, that bromine also came. Remember, what do we know about our HBr, HCl, HI? These are all strong acids, right? So keep that in mind. That's going to be a big factor here. Okay, so in this top example is sort of best case scenario because it really doesn't matter which side you add the bromine on, you're going to get an identical product, right? But what happens if I start out with an alkene that is not symmetrical like this, right? I have two different vinyl positions and they differ in terms of the amount of substitution, right? So this one has two groups on it, whereas this first one only has one. So the question is, which side gets the halogen? Okay, this is what we would call regioselectivity in these reactions. So it turns out that these addition reactions follow what's called the Markovnikov rule. Clearly some Russian scientists from back in the day. Oh yeah, look at that, 1869, really far ago. The Markovnikov rule is that the hydrogen is going to be added to the side that already has the most hydrogens. Another way to say that, and really the way that I want you to think about it, is the halogen is going to go on the more highly substituted carbon. Okay, so taking this example here, I have two vinyl positions, this guy and this guy. My more highly substituted one is this carbon here because it's already got more carbons bound to it. So that's the position where the bromine is going to go. The bromine is going to go, or the halogen is going to go on the more highly substituted carbon. This is again called a Markovnikov addition. You can hear this word a bunch. Okay, so again, take a second and see if you can't give me the product of this reaction here. This is going to be an addition reaction, but again, I'm going to have to look at my two vinyl positions and ask, where's the halogen going to go? It's going to go on the more highly substituted carbon. All right, so if we can just color code things here. This green one was my more highly substituted carbon than this, which is where the hydrogen went. And again, this is a Markovnikov addition. Turns out that you can get the opposite regioselectivity if you toss in a peroxide as well. So ROOR, ROOR, these are very kind of odd bonds in that you have oxygens single bound to one another. These are called peroxides. And it turns out that these will give you the opposite regioselectivity, or the anti-Markovnikov addition. Okay, so we can tune what our regioselectivity by either adding or withholding this peroxide. Again, just to color code things here. We will talk specifically about the reaction mechanism for these anti-Markovnikov additions in the presence of peroxide when we get to like chapter 10. We're not going to worry about those reaction mechanisms for now. We are going to focus on the reaction mechanism for the Markovnikov addition. So when you just have, for example, hydrobromic acid with your alkene. And I guess, again, just to hammer home, just HBr by itself, you'd have the Markovnikov product. Once you have a peroxide in there as well, you get to the anti-Markovnikov product. Okay, so I guess actually, before we get to the mechanism, let's just do a few examples. Again, you're going to look at your alkene and you're going to figure out your vinyl carbons. That's where the addition is going to be. In the case of HBr, it's going to, the halogen is going to go on the more highly substituted carbon. Whereas in the presence of peroxide, it will go on the less highly substituted carbon, right? So here, just to again be good about color coding versus here. Okay, and likewise, I guess I'll use green is my more highly substituted carbon. Blue is my less highly substituted carbon. So for this, I would have the Markovnikov addition, whereas in the presence of that peroxide, I'm going to have substitution on that less highly substituted carbon. Okay. So this is the different regioselectivities. So now let's focus on the mechanism. Hydrohalogenation will proceed through a carbocation intermediate. Okay, so the first step is you have your double bond acting as a base and accepting that acidic proton from the halogen. And this creates, let's just get rid of this for right now. And this will create a carbocation intermediate. All right, so carbocation intermediates, again, really important. The next step is then you have nucleophilic attack where that bromide ion or that halide ion is going to come and attack that carbocation. And that's what leads to our addition product. Notice that this explains why we have a Markovnikov addition or substitution of our halogen on the more highly substituted carbon, because those are the ones that will form the more stable carbocations. We can draw our free energy diagram for this, because again, we know that we have this carbocation intermediate, which means that we'll have this little dip up here at the top, followed by then that nucleophilic attack. That first step, that first proton transfer step, is going to have the highest activation energy. That's actually the rate determining step in these reactions. Okay, and again, this just illustrates why it gives us the Markovnikov product and not the anti-Markovnikov product, because it's all about that carbocation intermediate, right? So you have two choices of your carbocation intermediate. Once you have this attack from your double bond to that acidic proton, right? You got two choices. You can either form a secondary carbocation or a tertiary carbocation. We know that the more highly substituted carbocations are the more stable ones. So that's why we're only going to see this proceed through that Markovnikov pathway. And then again, the last step, just draw it out here, is going to be nucleophilic attack on that electrophilic carbocation. The last thing we want to talk about is the stereospecificity, right? So all that Markovnikov business is the regioselectivity, which constitutional isomer you're going to get. But now we got to think about stereochemistry. So for example, when we have addition of HCl to this particular alkene here, we've formed a new stereocenter, right? So the question is, well, what is the stereochemistry going to be? When we're talking about hydrohalogenation, it is not stereoselective, not stereo, meaning you're always going to get both enantiomers. All possible stereoisomers will be formed. In this case too, you'll get both the R and the S stereochemistry. And this has to do with that carbocation intermediate. We saw this before with carbocation intermediates. Remember, when a carbocation forms, it's actually a trigonal planar shape and have these electrophilic empty p orbitals sticking out both above and below. That means that the halogen can attack from either side. All right, so you will end up getting both stereoisomers. The last thing we got to worry about, because we are talking about carbocation intermediates, is the possibility for a hydride or a methyl shift. Okay, so remember, this is something that we see anytime we have carbocation intermediates, is the most stable carbocation wants to form. So if we have, for example, this alkene here, well, in that first step, our double bond will act as a base. It'll attack that acidic proton, and that'll kick off this chloride ion. And then we're left with this carbocation here. Well, we shift over this hydrogen, a hydride shift. What we're going to go is from a secondary carbocation to a tertiary carbocation, which is more stable. And so this is what will happen, and then our halogen or halide ion will then attack that more stable tertiary carbocation. Okay, so this is just one thing by virtue of the reaction mechanism of the hydrohalogenation. You got to watch out for the possibility of a hydride or a methyl shift. Hopefully we're all pretty good at spotting those at this point. Okay, so yeah, so I mean, basically when a carbocation can occur, it does occur. And in fact, it will be the major product, that rearrangement product. So it's something that we just always have to be on the lookout for. And if I ask what's the major product, you've got to make sure that you know that that rearrangement product is indeed going to be the major product of these reactions. All right, so at the end of each of these, I just wanted to give like a little bit of a cheat sheet here. These are the two main reactions that we talked about. So there's three things that I want you guys to always keep in mind. First of all, you got to be able to predict the products, right? That's just basics of any reaction. Can you predict what the products are? The other thing is, do you have to know the reaction mechanism? In the case of the hydrohalogenation all by itself, you do have to know that mechanism. You should be able to draw the reaction mechanism. Again, this is the one that's going to proceed through that carbocation intermediate. With regard to the reaction mechanism in the presence of this peroxide, you don't have to know that. We'll get to that in chapter 10, but for now, that's not something I expect you to know. Okay, the other thing is regioselectivity. These are Markovnikov additions. With regard to regioselectivity, these are anti-Markovnikov in the presence of peroxide. All right, and then lastly, what we got to worry about is stereoselectivity. These are not stereoselective. So actually, we'll just put no. Not stereoselective, you'll always get your mixture of R and S because of the nature of that carbocation intermediate. And then down here, these are also not stereoselectives. Okay, so this is just a summary of these two reactions, which were our main focus of this hydrohalogenation lecture.